What happens when the sun does not produce one eruption, or even two, but launches a rapid-fire series of coronal mass ejections from the same active region over several days? That is the question scientists have been asking after more than 5 solar storms began racing toward Earth at nearly the same time. The first was expected to arrive before noon UTC on July 3rd, with additional impacts following in stages through July 6th. NOAA's Space Weather Prediction Center issued a watch for a moderate G2 geomagnetic storm, while observers prepared for auroras that could become visible as far south as New York, Wisconsin, and Washington state. During that same period, the sun produced 10 solar flares within 24 hours from a single region. That sequence happened 3 weeks ago, but the sun has not gone quiet. As of July 23, 2026, NOAA was forecasting that 2 coronal mass ejections, or CMEs, launched on July 20th and July 21st, could deliver glancing blows to Earth's magnetosphere. Those impacts could produce G1 minor geomagnetic storm conditions on July 24th and July 25th, with activity gradually easing as a separate coronal hole stream weakens by July 25th. This means 3 distinct solar disturbances are expected to reach Earth during the same week. The first 2 come from CMEs that left the sun on July 20th and 21. The third comes from a coronal hole high-speed stream, a completely different phenomenon that is sending accelerated solar wind toward Earth from another region of the sun. 3 mechanisms, 3 arrival windows, and 1 magnetic field receiving all of them within a narrow period. NOAA's forecast describes conditions progressing from unsettled to active and then toward G1 storm levels across 4 consecutive days. So this is not the quiet late July period that a calendar might have suggested at the beginning of the month. It is the latest development in a larger solar activity story that began as the sun moved into the maximum phase of solar cycle 25. This maximum has already produced more X-class flares, more CMEs, more geomagnetic storms, and more mid-latitude aurora sightings than many comparable periods since the early 2000s. To understand what this week's 3 disturbances could mean for power grids, GPS systems, satellites, radio communications, and aurora watchers, it helps to separate the events and understand how they work. The most closely monitored components are the CMEs launched on July 20th and July 21st. A coronal mass ejection is a vast cloud of magnetized plasma expelled from the sun's outer atmosphere, known as the corona. During a total solar eclipse, the corona appears as the pale, pearly halo surrounding the darkened solar disk. That atmosphere is threaded with powerful magnetic field lines. Under certain conditions, those fields become increasingly twisted and unstable. When the magnetic configuration reaches a critical threshold, the field lines can suddenly break and reconnect in a process called magnetic reconnection. This releases an enormous amount of stored magnetic energy. Some of that energy accelerates electrons to nearly the speed of light, producing the burst of X-rays that we detect as a solar flare. Another portion drives a massive bubble of plasma and magnetic field outward from the corona. Depending on the eruption, a CME can travel at several hundred kilometers per second or accelerate to several thousand. The CMEs launched on July 20th and 21 came from active regions that NOAA had been monitoring throughout July because they remained capable of producing additional flares. Forecast models indicated that both eruptions could pass close to Earth on July 24th and 25, bringing unsettled to active conditions and a chance of G1 geomagnetic storms. The word glancing is important here because it has a specific technical meaning. A glancing blow occurs when a CME passes near Earth without striking the planet directly. The center of the plasma cloud is offset from Earth's position, so only the leading edge clips one side of the magnetosphere instead of hitting it head-on. A direct impact would be more powerful. Full halo CMEs appear from Earth as complete rings expanding around the solar disk, a sign that the eruption is traveling almost directly toward us. These events can produce the most severe geomagnetic storms because they deliver more plasma and magnetic energy into Earth's magnetic environment. A glancing CME is usually weaker, often producing G1 or G2 conditions, but weaker does not mean irrelevant. Even a G1 storm can generate auroras at unusually low latitudes, interfere with high-frequency radio communication near the poles, cause minor fluctuations in power grid voltage, and increase atmospheric drag on satellites in low Earth orbit. The effects may not be dramatic for most people on the ground, but satellite operators, power grid managers, pilots, and radio users still have to monitor them closely. And this week's situation is more complicated than a pair of passing CMEs. At almost the same time, a coronal hole high-speed stream is moving through Earth's magnetic environment. To understand why that matters, we need to look at how a coronal hole creates a very different kind of disturbance. A coronal hole is an area of the sun's corona where magnetic field lines remain open rather than looping back into the solar surface. Because those lines extend outward into space, The solar wind plasma above them is not held in place as tightly as it is in regions with closed magnetic loops. The plasma can escape more freely and accelerate to speeds much higher than the surrounding solar wind. The resulting flow is called a coronal hole high-speed stream. It is a sustained jet of fast solar wind that moves through the solar system as the sun rotates. Since the sun completes one rotation in roughly 27 days, the stream sweeps across space in a broad, rotating pattern. Whenever one of these fast streams reaches Earth, it can compress the magnetosphere and trigger periods of geomagnetic activity that last for days rather than only a few hours. That difference in duration is central to this week's forecast. The CMEs from July 20th and 21 can deliver a sudden shock. Their arrival compresses the magnetosphere, increases the pressure on Earth's magnetic field, and introduces a surge of plasma and magnetic flux. The coronal hole stream can then keep the environment disturbed after the initial CME impact begins to fade. When these two sources arrive within the same narrow window, forecasters describe the situation as a compound geomagnetic event. The CME provides the initial push, while the high-speed stream helps sustain the disturbance. The overall event can therefore last longer and behave differently from either source acting alone. Now consider what the forecast levels actually mean for people who are not solar physicists. NOAA uses a 5-level scale for geomagnetic storms, ranging from G1 to G5. G1 is classified as minor. G5 is extreme, the category associated with the strongest storms and the greatest potential for serious disruption. The current forecast for July 24th and 25 is G1, the lowest storm level on that scale. But minor does not mean meaningless. The most severe modern example occurred on March 13th, 1989, when a G5 storm caused a 9-hour blackout across the Canadian province of Quebec. Geomagnetically induced currents entered the Hydro-Quebec power system, which had not been designed to withstand that level of disturbance. A G1 storm is nowhere near that category under ordinary circumstances, but it can still create conditions that operators need to watch. At G1 and G2 levels, possible impacts include power grid fluctuations and voltage alarms in high-latitude systems, unusual satellite orientation behavior, greater drag on low Earth orbit spacecraft, fading of high-frequency radio signals near the poles, and auroras visible much farther south than usual. Each effect matters to a different group of people. Power fluctuations during a G1 or G2 storm are not the same as the widespread outages associated with an extreme event. Modern power systems in northern Canada, Scandinavia, northern Russia, and Alaska are designed to respond to these conditions. Grid operators monitor geomagnetic indices in real time and follow procedures for adjusting power generation, switching operations, and system loads when activity rises above certain thresholds. The concern is not that a normal G1 storm will suddenly collapse an entire grid. It will not. The concern is that even a small geomagnetic disturbance can reduce the safety margin when a grid is already under pressure. During a heat wave, for example, electricity demand may be close to its daily peak. A system operating near its limit has less room to absorb additional stress, even if that stress is modest. Satellites face a different problem. Geomagnetic activity heats the upper atmosphere, causing it to expand. At low Earth orbit altitudes, the atmosphere then becomes denser than expected. That extra density increases drag on satellites and gradually lowers their orbits more quickly than standard predictions assume. Operators of large, low Earth orbit constellations, including Starlink, must account for that additional drag. Starlink now operates more than 7,000 satellites in the altitude range most affected by geomagnetic storm-related atmospheric expansion. Operators may need to revise station-keeping plans and use more fuel to maintain the correct orbits. During the powerful G5 storm in May 2024, Starlink engineers described the challenge of managing increased drag across the constellation at the same time. Radio communications are also affected, especially at high latitudes. Aviation and maritime operators still rely on high-frequency radio for long-distance communication in areas where other systems may not work reliably. This is particularly important for aircraft flying polar routes between North America and Asia. When a geomagnetic storm increases ionospheric absorption, high-frequency signals can fade or disappear over polar regions. Pilots and air traffic control centers then have to shift to alternative communication methods. This is not normally a safety catastrophe, because polar flights have procedures for handling radio disruptions, but it adds complexity to one of the world's busiest long-haul aviation corridors. GPS is influenced through another mechanism. Satellite navigation signals pass through the ionosphere, and the amount by which they are refracted depends on the density and behavior of the ionospheric electrons. During a geomagnetic storm, that environment becomes more variable. The resulting changes introduce timing errors into GPS signals, and even tiny timing errors can affect calculated positions. For standard navigation, G1 level effects may amount to only 1 or several meters of positioning error, which most users would never notice. But that difference can matter in precision agriculture, construction surveying, and aviation approaches that depend on centimeter-level accuracy. The storm may be minor on NOAA's scale, yet still important for systems that require extremely precise location data. For most people, however, the most visible consequence is the aurora. And this week's conditions may offer a genuine opportunity to see it. During the earlier sequence in July, G2 conditions were expected to push the aurora far enough south for possible sightings in places such as New York, Wisconsin, and Washington state. The G1 conditions forecast for July 24th and 25 are weaker, but they may still move the auroral oval toward approximately 55 degrees geomagnetic latitude. That is roughly the latitude of the United States-Canada border across parts of the Great Lakes region. At G1 levels, the northern lights are most likely to appear across Canada, Alaska, Scandinavia, Scotland, and the northern edge of the continental United States. If the storm briefly reaches stronger peaks, when the KP index rises to 5 or touches 6, the aurora oval can expand farther toward the equator. Observers in the northern tier of the United States may then see a glow along the northern horizon. At those lower latitudes, the display may not look like the bright, overhead curtains often photographed in Alaska or northern Scandinavia. Instead, viewers may see a soft green or reddish glow low in the sky. The best viewing conditions usually come after local midnight, far from city lights, with clear weather and an unobstructed view toward the north. There is one important limitation. An aurora forecast is never a guarantee of a spectacular display. A forecast for G1 conditions describes the expected strength of the geomagnetic disturbance, not exactly what people will see from the ground. The visual result depends heavily on the magnetic orientation of the incoming solar material, especially the direction of its BZ component. If the BZ component points strongly southward, the magnetic field carried by the CME can connect more efficiently with Earth's magnetic field. That allows more energy to enter the magnetosphere and flow toward the polar atmosphere, increasing the chance of a bright aurora. If BZ remains northward, the coupling is weaker, and the storm may produce a less impressive display than the original forecast suggested. This uncertainty brings us back to the larger question. Why are 3 solar disturbances reaching Earth during 1 week in late July 2026? The answer lies in the position of the Sun within its approximately 11-year activity cycle. The solar cycle alternates between solar minimum and solar maximum. During minimum, sunspot numbers are low, major flares are uncommon, and the solar wind is generally steadier. During maximum, the Sun's magnetic field becomes more complex and dynamic. Sunspots become more numerous, active regions grow more unstable, and powerful M-class and X-class flares become more frequent. CMEs also become more common, increasing the likelihood of geomagnetic storms at Earth. Solar Cycle 25 entered its maximum phase in late 2024 and is expected to remain highly active through at least the middle of 2026. Some forecasts extend the broader influence of the maximum into 2027. That does not mean every day will bring a major flare or an Earth-directed CME. Solar maximum is not a constant explosion. Instead, it produces clusters of activity separated by quieter intervals, while the overall probability of significant events remains much higher than during solar minimum. Active region 4479 became a major part of that story. It produced the X1.1 flare and full halo CME on June 30th, 2026, beginning the rapid sequence of solar eruptions described earlier. NEOAA continued to identify the region as a flare risk area into early July, showing that the region remained magnetically complex even after its most dramatic eruption. At the same time, coronal hole high-speed streams create a repeating source of activity that does not require a spectacular flare. These streams can return approximately every 27 days following the Sun's rotation. That recurrence is significant because the same coronal hole that produced the high-speed stream affecting Earth this week may rotate back toward the Earth-facing side of the Sun in about 27 days. If the coronal hole remains open, the high-speed stream could return again in late August. Coronal holes often survive across several solar rotations, so a repeat disturbance would not be surprising. This is not a prediction based on guesswork. It follows from the geometry of the Sun's rotation and the recurring behavior of open magnetic regions. Scientists are therefore watching more than one storm. They are watching the pattern. The significance of late July is not that one G1 event is unusually dangerous. It is that repeated activity from CMEs, active regions, and coronal holes is occurring within a solar maximum that is already producing a high number of disturbances. Space weather physicist Dr. Timothy Skov has noted that multiple Earth-directed CMEs arriving in rapid succession are consistent with a highly complex solar active region. When such regions cross the Earth-facing side of the solar disk, the risk of additional X-class flares can remain elevated for an extended period. That observation helps define what happens next. There are 2 different timescales to consider. The The first is immediate, the roughly 48-hour window from July 24th to July 25th, when the two CMEs may interact with the existing coronal hole stream and generate G1 conditions. The second is much longer, the remaining period of solar cycle 25's maximum phase, when more active regions will rotate into view and produce new opportunities for flares and CMEs. In the immediate window, high-latitude grid operators will continue monitoring geomagnetic indices. Satellite teams will track atmospheric drag and orbital changes. Aurora observers across Canada and the northern United States will follow cloud conditions and KP forecasts. High-frequency radio users will prepare for possible propagation disruptions. None of this means that a disaster is unfolding. It is the normal operational response to a planet moving through a period of heightened solar activity. But to understand why scientists remain attentive, we have to look beyond this single week and examine what repeated moderate storms could mean over the rest of the solar maximum. Throughout the remainder of solar cycle 25's maximum, the activity level that produced the rapid-fire eruptions in early July, the G1 watches in late July, and the continuing flare risk from Earth-facing active regions is expected to continue. The pattern will not be uniform. There may be quiet stretches, lasting days or weeks, followed by clusters in which several eruptions occur close together. Even so, the average number of significant events remains much higher during solar maximum than during solar minimum. That includes M-class and X-class flares, Earth-directed CMEs, and geomagnetic storms of varying strength. The number of named geomagnetic storms formally tracked by NOAA during 2025 and 2026 is already well above the comparable period of the previous solar cycle. That leads to a broader question. What happens when moderate solar storms continue affecting Earth's technological systems over an extended period? Every G1 or G2 storm that reaches the magnetosphere deposits energy into the upper atmosphere. That energy heats and expands the atmosphere, increases the orbital decay of low Earth orbit satellites, induces small electrical currents in power grid infrastructure, and can reduce GPS accuracy for hours or even days. Each individual event is manageable. The concern raised by power grid engineers and satellite operators is the cumulative effect of many moderate disturbances during a sustained solar maximum. Repeated drag events can increase satellite fuel consumption. Frequent GPS disruptions can complicate precision operations. Repeated geomagnetically induced currents can place additional stress on certain parts of power infrastructure. This is why NOAA's space weather action plans, along with equivalent European frameworks, focus not only on predicting individual storms, but also on preparing for a range of possible conditions. The larger statistical reality is that at least one major extreme event is likely to occur before the current solar cycle ends. That does not mean scientists know when it will happen, or whether it will strike Earth directly. It means the probability rises as the cycle produces more active regions and more powerful eruptions. The last G5 extreme geomagnetic storm occurred in May 2024. It was powerful enough to create widespread auroras and disrupt some technological systems, but it was not as intense as the historic Carrington event of 1859. That 19th century storm remains the benchmark used in worst-case planning. Scientists estimate that the Carrington event may have been 3 or 4 times more powerful than the May 2024 storm. If a Carrington-level event reached Earth today, its consequences would be fundamentally different from those experienced in 1859. Modern society depends on satellites, GPS timing, digital communication, aviation networks, undersea infrastructure, and interconnected electrical grids on a scale that did not exist during the 19th century. The same physical disturbance could therefore create far more complicated consequences in the modern world. That scenario is not being forecast for July 24th or 25. The expected G1 conditions are at the lowest end of NOAA's storm scale, and the two CMEs are expected to deliver glancing impacts rather than a direct strike. But the frequency of events like this is precisely why scientists are paying close attention. After 3 relatively modest disturbances in 1 week, the next major eruption from a complex active region could behave very differently. The relationship between storm category and potential impact is not perfectly linear. A small increase in geomagnetic activity does not always produce a proportionally small increase in consequences. A storm's intensity, duration, magnetic orientation, location, and interaction with existing conditions all matter. A direct CME impact with a strongly southward magnetic field can transfer energy into Earth's magnetosphere far more efficiently than a weak or poorly oriented event. That is why NOAA updates its space weather forecasts every 3 hours. As the July 24th and 25 arrival windows approached, forecasters would revise their estimates using observations from spacecraft positioned between Earth and the Sun. The ACE and DSCOVR satellites occupy or monitor the region around the L1 Lagrange point, where they can measure the solar wind before it reaches Earth. The most important measurement is the BZ component, which describes the north-south direction of the incoming magnetic field. A southward BZ allows the solar magnetic field to connect efficiently with Earth's field. That connection opens the door for more energy to enter the magnetosphere and increases the likelihood of a stronger storm. A northward BZ has the opposite effect. The incoming field couples less efficiently with Earth's magnetic field, and the resulting disturbance may be weaker than earlier models predicted. The crucial information becomes available only shortly before arrival, often around 30 to 60 minutes before the solar material reaches Earth. That short warning period explains the unusual rhythm of space weather forecasting. Scientists can observe an eruption leaving the sun days in advance and estimate its arrival time, speed, and possible trajectory. But the final answer about storm intensity may not arrive until the CME is almost at Earth. Forecasters and operators therefore watch the data in real time, knowing that the most important detail has not yet been measured. For Aurora watchers, this means that a promising forecast can still produce a disappointing night. For satellite operators, it means that orbital decisions may need to be made quickly. For grid managers and radio users, it means staying ready to respond when the magnetic measurements confirm what the models could only estimate. The July sequence is manageable, but it is also a useful reminder that space weather is not a single event with a simple beginning and end. It is a chain of eruptions, streams, magnetic interactions, and changing conditions. To see what scientists are truly watching, we need to follow that chain to its final question. What does this pattern reveal about the months ahead? The immediate question is whether the CMEs launched on July 20th and 21 will produce the predicted G1 disturbance when they reach Earth. The broader question is what their arrival, combined with the coronal hole stream, tells scientists about the direction of solar cycle 25. The answer will depend on the data collected during the event. If the CMEs arrive as expected and produce only weak or moderate disturbances, that information will help refine forecasts for similar events later in the cycle. If the magnetic field turns strongly southward and the storm becomes stronger than predicted, scientists will examine why the models underestimated the coupling between the incoming plasma and Earth's magnetosphere. Every event provides another measurement of the sun's behavior. Active regions can change rapidly, and their eruptions do not always travel through space in a perfectly predictable way. A CME may slow as it interacts with the solar wind, or it may be deflected by other magnetic structures. Two eruptions launched at different times can also merge, interact, or arrive close enough together to produce a more complicated disturbance than either would create alone. That is one reason the early July sequence was so important. It was not a single eruption, but a chain of CMEs leaving the same active region over multiple days. The storms then reached Earth in stages, creating a prolonged period of activity rather than one isolated impact. The same active region also produced 10 flares in a 24-hour period, demonstrating how quickly solar conditions can change when a region becomes highly unstable. The late July forecast is different in scale but connected in structure. Two CMEs are arriving after leaving the sun on consecutive days, while a high-speed solar wind stream is already affecting the magnetosphere. The combined result may not be an extreme storm, but it offers scientists a valuable opportunity to study how different solar disturbances interact. That interaction matters because future forecasts will not always involve one cleanly defined CME. The sun may send several eruptions toward Earth while a coronal hole stream is already in progress. The more accurately researchers understand these compound events, the more effectively operators can prepare for them. Power grid managers do not need to know only whether a storm is classified as G1 or G2. They also need to know how long it may last, whether its strongest phase will occur during high electrical demand, and which regions are most exposed to geomagnetically induced currents. Satellite operators need estimates of atmospheric expansion and drag, not just a general warning that a storm is coming. A constellation operator may need to decide whether to change a satellite's attitude, delay a maneuver, increase orbit maintenance activity, or conserve fuel for future corrections. Those decisions become more complicated when repeated disturbances occur close together. A single moderate storm may require a small adjustment, while a sequence of storms can gradually alter operational plans across an entire fleet. GPS users experience a similar difference between an isolated disruption and a repeated pattern. Most people may not notice a 1-meter error in a standard navigation application. But precision agriculture, surveying, construction, scientific measurement, and aviation systems often work at a level where small errors matter. If ionospheric conditions remain unstable for an extended period, those users may need to rely on correction systems or alternative methods for longer than expected. Radio operators also monitor duration and repetition. A brief period of high-frequency fading may be manageable, but repeated disruptions along polar routes create additional work for pilots, dispatchers, and air traffic control centers. Alternative communication systems exist, yet each one has its own range, coverage, and operational limits. For the public, the most immediate sign of solar activity may be the aurora. A moderate storm can produce a remarkable display if the magnetic conditions align correctly. But the same forecast can result in only a faint glow or no visible aurora at all if clouds, light pollution, or an unfavorable BZ orientation interfere. That uncertainty is not a weakness in the science. It reflects the difficulty of predicting a magnetic field that is still traveling millions of kilometers through space. Solar wind models can estimate when a disturbance may arrive and how strong it might be, but the final interaction depends on conditions that become clear only near Earth. The upcoming measurements from ACE and DSCOVR will therefore be critical. As the spacecraft detect the actual density, speed, temperature, and magnetic orientation of the incoming solar wind, forecasters can update the expected storm level. A southward BZ would signal stronger coupling and potentially brighter auroras. A northward BZ would suggest that much of the incoming energy may remain outside the magnetosphere. This is why the space weather community watches these arrival windows with such intensity. The eruption has already happened on the Sun, but the outcome at Earth is still being determined by the details of its journey. The forecast provides the framework. The real-time measurements reveal what the storm is actually carrying. This week's 3 disturbances are therefore not a warning that society is about to lose power or that satellites are about to fall from orbit. They are a manageable episode within an active solar cycle. At the same time, they are a clear demonstration of why scientists continue watching the Sun closely, because the next event may not be as modest or as indirect. The most important point is that this week's activity should be understood as part of a pattern rather than as an isolated emergency. The CMEs launched on July 20th, and the 21st of may produce G1 geomagnetic conditions when they graze Earth's magnetosphere. The coronal hole high-speed stream may extend that activity after the initial impacts pass. Together, they create a compound event that can affect satellites, GPS accuracy, high-frequency radio, power grid operations, and aurora visibility, even though the expected storm level remains relatively low. In the short term, operators will continue watching the data through the July 24th and 25 arrival window. High-latitude power grids will monitor geomagnetic indices and voltage behavior. Satellite teams will track atmospheric density and orbital drag. Aviation and maritime users near the poles will remain alert for high-frequency communication problems. Aurora observers across Canada, Alaska, Scandinavia, and the northern United States will look for clear skies and a favorable magnetic orientation. The outcome will depend heavily on BZ. If the incoming field turns southward, energy can flow efficiently into Earth's magnetosphere, potentially strengthening the storm and improving the chances of visible auroras at lower latitudes. If BZ remains northward, the interaction will be less efficient, and the event may remain weaker than forecast. That final information becomes available only about 30 to 60 minutes before the solar material reaches Earth, which is why the most important phase of the forecast happens so close to arrival. In the medium term, solar cycle 25 is expected to remain active through at least the middle of 2026, with some forecasts extending the influence of solar maximum into 2027. Additional active regions will rotate across the Earth-facing side of the Sun. Some may produce only small flares, others may launch Earth-directed CMEs, and the probability of stronger events remains elevated while the solar magnetic field is this complex. The coronal hole stream may also return. Because the Sun rotates approximately once every 27 days, a persistent coronal hole can send another high-speed stream toward Earth when it comes back around. If the current hole remains open, another period of enhanced geomagnetic activity could develop in late August. That possibility follows from the Sun's rotation and the known behavior of coronal holes, rather than from speculation about a particular eruption. Scientists are watching the frequency and clustering of these events because repeated moderate storms reveal how technological systems respond to sustained solar activity. Every storm deposits energy into the upper atmosphere, increases drag on low Earth orbit satellites, introduces currents into electrical infrastructure, and can make GPS positioning less reliable. Each event may be manageable on its own, but the cumulative effect becomes more important when disturbances arrive repeatedly. The larger concern is not that a G1 storm will suddenly produce a civilization-ending blackout. It will not. The concern is that the current period of increased activity raises the odds of a much stronger event before solar cycle 25 ends. The May 2024 G5 storm demonstrated that extreme geomagnetic activity remains possible, while the Carrington event of 1859 shows how powerful a solar storm can become under the right conditions. A Carrington-level storm today would affect a world far more dependent on interconnected technology than the world of 1859. Satellites, navigation networks, digital communications, aviation, and power grids would all face different forms of stress. But that is not the forecast for this week. The July 24th and 25 event remains at the low end of NOAA's scale, and the expected CME impacts are glancing rather than direct. The significance lies in the contrast. 3 relatively modest disturbances can arrive in 1 week, yet the next eruption from a complex active region could be faster, stronger, and aimed more directly at Earth. The difference between those outcomes is not determined by the number of events alone. It depends on CME speed, magnetic structure, trajectory, duration, and especially the orientation of the field when it arrives. That is why NOAA's Space Weather Prediction Center updates its forecasts every 3 hours. The sun does not follow a monthly calendar, and it does not provide a final answer until the plasma is close enough for spacecraft to measure it directly. ACE and DSCOVR serve as an early warning system, observing the solar wind at the L1 point before it reaches Earth. Their measurements can turn a broad forecast into a near real-time assessment. So, what happens next? In the immediate future, scientists and operators will watch the 3 disturbances move through Earth's magnetic environment and compare the actual conditions with the forecast. In the coming weeks, they will monitor returning coronal hole streams and new active regions. Across the remainder of the solar maximum, they will continue building a clearer picture of how frequently the sun produces clustered eruptions and how strongly those eruptions affect modern infrastructure. This week's triple hit is manageable. It may even give Aurora watchers an opportunity to see the northern lights farther south than usual. But it is also a data point in a much larger sequence, one that is still being written by a star that does not consult the forecast calendar before deciding what to do next. Subscribe and turn on notifications for continuing space weather updates. NOAA revises its forecasts every 3 hours, while DSCOVR and ACE measure the incoming solar wind in real time. When the BZ readings arrive and the actual storm level becomes clear, the next update will show whether this week's 3 solar disturbances remained minor, or revealed something stronger developing on the horizon.